In this video, I'm going to discuss some basics in electricity to get you started. We need electricity to power many of our household items. Electricity brings comfort to our lives. The utility grid is our main source of electricity. Unfortunately, in many parts of the world, it is unreliable. Wind energy is still expensive, and there isn't always a wind blowing. Solar is coming down in price, but you need to have a good location for your panels, and the sun is available only during the daytime. Energy storage is expensive, and it's complicated. I'll discuss the components on a follow-up video. For now, let's stick to basics. When we think of clean energy, we certainly don't think of this. Let's take a closer look at how we came to have our electrical grid. In the late 1800s, Edison and Westinghouse were competing to provide electricity power systems. The battle between these two is famous, and there are many websites where you can learn their story. Edison was promoting DC power systems, and Westinghouse AC power systems. Initially in the US, DC stations had the early advantage and were being installed in many US cities. The problem with these DC stations is that you needed so many of them, as there was no elegant way to convert one DC voltage to another. I'll discuss AC versus DC later. The result is that you needed to be very close to a power station in order to use the electricity. Along comes Nikola Tesla. Tesla, who had previously worked with Edison, invents an AC power system and begins working with Westinghouse. Tesla uses an earlier invention of the transformer to gain an advantage. Using transformers to raise and lower voltages in AC proved to be advantageous, as high voltage AC systems could transport AC electricity over huge distances without incurring huge losses. This meant fewer power stations. Let's talk about two types of voltages. AC means alternating current. DC means direct current. In direct current, DC, the electric current only flows in one direction, such as the current flowing out of a battery. In AC, or alternating current, the current changes direction many times per second. Half the cycle has positive voltage and half has negative voltage relative to ground. In Europe, the electricity cycles up and down 50 times each second, and in North America, it's 60 times each second. What does it mean when we say we have a 120 volt system in North America? 120 volts AC is an RMS voltage. RMS stands for root mean square. That means the equivalent of having 120 volts direct current, but it's not actually 120 volts. That's only the average. How do we convert the AC voltage to find this RMS voltage? Peak values for a pure sine wave can be calculated from RMS values using the formula V peak equals V RMS times the square root of 2. This means that the peak voltage in North America, 120 volts RMS, is 120 times the square root of 2, or approximately 170 volts peak. This means that the peak voltage swings between 170 volts positive to 170 volts negative 60 times each second. In Europe, the 230 volts AC, or 230 volts RMS, means that the peak voltage is approximately 320 volts. Remember that in previous slides we were concerned about losses in an AC versus a DC power system. So where do the losses in the distribution of electricity come from? P equals V times I is the formula for calculating power. P stands for power measured in watts. I stands for current and is measured in amps. Current is the flow of electrons, basically the amount of electrons flowing through a cable. Think of this as the volume of water going through a water hose. V stands for voltage, or electromotive force, and is measured in volts. Think of voltage as the amount of force pushing the electrons or the pressure pushing water through a hose. From Ohm's law, we know that V equals I times R, where R stands for resistance. Resistance is in opposition to the flow of the current. Basically, electrons are colliding with atoms in the cable. The greater the resistance, the more often there are collisions. Cables have an associated resistance according to their material. Cable diameter also has an effect on resistance. Larger diameter cables have a low resistance, and a small diameter cable has a high resistance. Using the water hose example, a large diameter hose would offer low resistance to the water, and a small diameter hose would offer a greater resistance. In this formula, V equals I times R, we see that it is the voltage that will vary depending on the values of I and R. Remember that the electrons are inhibited by resistance, but the number of electrons, or the current, stays the same. Now that we understand this, let's get to the losses. We calculate the voltage drop by the formula of V drop equals I squared times R. Often I am told that DC current has higher losses than AC, and that is why DC power systems lost the battle. That's not true at all. Please tell me where to plug AC or DC voltages into the formula V drop equals I squared times R. The reason that AC won was because AC voltage could be raised and lowered using transformers. The result was that AC could be transported over long distances in the kilovolt range. There was no easy way to do this for DC voltages. Look again at the P equals V times I formula. Raising the voltage means that you can lower the current proportionally and still achieve the same power. 10 volts times 10 amps equals 100 watts. 100 volts times 1 amp still equals 100 watts. But examine the V drop formula. A smaller current means a much smaller loss. Because the current is a squared value, 1/10 the current means 1/100th the loss, 10 amps squared compared to 1 amp squared. Or 1/100th the current means 1/10,000th the loss, 100 squared compared to 1 squared. Raising the voltage and lowering the current has a huge effect. We have another issue. Resistance also increases with cable length. What that means in practical terms is that given the same diameter cable, the longer the length of cable, the higher the loss. This makes the high DC losses even worse with distance. Once AC systems were proven, DC never stood a chance. Nowadays we have the methods to create and transport high voltage DC, but for now it's too late as the AC infrastructure is already in place. Power factor. This is a complicated topic, so I will keep it simple. Not all of the power in AC systems is usable. Power that can be used by a load is called true power. AC motors are induction motors. This is called a reactive load. Induction motors cause the current to be out of phase with the voltage. The power portion that is absorbed and returned in a reactive load is known as reactive power. Reactive power is measured in the unit volt-amps reactive, or VAR. Reactive power is wasted power as loads cannot use this. To compensate, power companies use what is called VAR compensation to bring the current and voltage back in phase. Why is it important to know this? Many parts of the world lose electricity every day. Households have backup systems that keep the lights and TV or radio on. However, if they try to operate a fridge, it tries to start and shuts down. They all know this, but few know why exactly. This is because the fridge motor starting up will cause the current and the voltage to go out of phase. The true power available will drop, and the fridge's electronics will detect that the usable power is too low and shut down to protect itself. Now that you are familiar with some of the basics, in part 2, I will discuss some of the components used in renewable energy systems.